Okay, this is lesson 6.5, and this is about exponential models. So what is an exponential model? Well, an exponential model represents quantities that change at a constant growth or decay rate. So while linear models had constant rates of change, that was like a constant addition. We were constantly adding. When you're looking at an exponential model, this is where it's constant multiplication. So we're constantly multiplying by something. So a different type of growth or decay. So when we're looking at a table of values, you're looking to see that the growth or decay factors are constant. I'm going to show you how to do that. The graph must resemble an exponential curve, and we'll look at what those look like and how they're different from parabolas. And finally, the equation should be written in the form y equals a b x, with the exponent being the x. I'm going to rewrite that because that looks terrible. Y equals a b x, where a is the initial value, b is the growth or decay rate, and notice that the exponent is the variable. So two types of exponential models. We can have growth or decay. We have exponential growth. That means the relationship is growing when b is bigger than 1. So when the base is a number that's bigger than 1, like 2 or like 1.5 or 4. If the base is a number between 0 and 1, that's called decay. And the reason why is when you constantly multiply by something bigger than 1, the number you start with gets bigger, even if it's something really small like 1.1. If you take the number 10 and you multiply by 1.1, you get 11. That number gets bigger. If you multiply by something less than 1 but bigger than 0, the number will get smaller, like 0.9. If we started with 10 and multiply by 0.9, we get 9. Multiply by 0.9 again, we get 8.1. The number keeps getting smaller and smaller and smaller. So here's two equations. One is growth and one is decay. Our first model is growth. And that's because b is greater than 1. Our second model is decay. And that's because b is between 0 and 1. So how much is this growing by and how much is this decaying by? Well, to find out, we either subtract from 1 or subtract by 1. So in this example, this is a growth example, so it's bigger than 1, so the question is how much bigger than 1? So if you want to know the growth rate, you look at how much bigger than 1 this number is. And to do that, you just take the number and you subtract 1. And that's 0.071. If we convert that decimal to a percent, that's 7.1%. So whatever this is modeling, it's growing by 7.1%. The A, being the initial value, 500, means that 500 is growing by 7.1% constantly. Decay. This number is less than 1. So if we want to figure out the decay rate, we don't subtract 1 because we're going to end up with a negative. We actually subtract from 1. So we see how much under 1 it is. And in this case, we get 0.08, which, if we turn into a percent, is 8%. So in this example, the 500 would be getting smaller by 8%, constantly getting smaller by 8%. All right, let's look at a table, a graph, and an equation and pick out the exponential ones. So here's our table. We have two of them. We can look at the first and second differences, but if we didn't get a constant first difference or second difference, we wouldn't see that the model is exponential. But let's take a look anyways. First difference. If we look at the first difference, this is going down, it's going down by 10. This one's actually going down by 10, and this one's going down by 10. So this model is linear. This means linear. So what we can say is this is not exponential. Our second table, let's find out. Well, if we look at first differences, this time we're going down by 12.8, and then by 16, and then by 20. Hey, first differences aren't the same. So now we can look at second differences, see if it's quadratic. We get 3.2 and 4. Hey, so it's not quadratic either. So what we can do, our test for exponential is not a third difference, it's something called the y ratio. And to do y ratio, instead of subtracting consecutive y values, we divide them. So we're going to compare these two y values first. We're going to do 64, always the second one, divided by the first one. And we're going to look for an answer. And then we're going to compare these two, 80 and 64. So we would do 80 divided by 64, get an answer. And then we're going to compare these two, 180, and we're going to get an answer. Well, if we do all three of these divisions, we actually get the same answer. And this, because we have a constant y ratio, this tells us that we're constantly multiplying by something. In fact, what we're constantly multiplying by is 1.25. So we're growing, because these numbers are getting bigger. How much are we growing by? Well, we're growing because we're multiplying by 1.25 constantly, which is 0.25 above 1, so this is a growth rate of 25%. So these numbers are getting 25% bigger every time. But all we need to know is that if we do a y ratio test and we get constant y ratio, we can conclude that this is an exponential relationship. What if we do first difference, second difference, and y ratio, and none of them are constant? It just means it's not perfectly linear, quadratic, or exponential, and you may choose to pick the one that's closest or the best model, or you may choose to conclude that it's none of them, and that's actually what our next lesson is going to be on, 6.6, choosing a model. So stay tuned for that one. Next, we're going to look at graphs. Our first graph is clearly not exponential. And why is it not exponential? Well, it's because it's a line. It has a constant rate of change. But our second one might be exponential, but it could be a parabola as well. It could be part or half of a parabola. So how do you tell? Well, what you do is you look at the steps on the curve. And what do I mean by that? I mean, on your x-axis, start at 0, go to 1, and then go up until you hit the curve. So that's one step on the x, and the question is how much should you go up on the y? Well, 0, 1, 2, we went up 1, so our first step's 1. Let's look at the next step. Over to 2, up to the curve. This time we went up 2 boxes, and we'll do one more step. Over to 3, up to the curve, and then go count the steps. 1, 2, 3, 4. That's 4. So this is an exponential model, and you might be asking why. The reason is because the steps keep getting bigger by a multiple. 1 times 2 is 2. 2 times 2 is 4. The next step we would expect would be 8. The next step, 16. Because these numbers are getting bigger by a multiplier, that makes it exponential. If these numbers were going up like 1, 3, and 5, they're just going up by adding 2 every time, that would be a parabola. So this is exponential, and it's because of exponential growth. I should write exponential there. I'm just going to say growth. It's a growth model times 2, because we keep getting bigger by a factor of 2. And E and F. Equation E here, equation F here, one of these is exponential. Well, this one, it's got an x squared, so that's called degree 2, and we know that's quadratic. So this one is not exponential. But this one is exponential. Why? It's because of the exponent. The exponent is the variable. If you have an exponent that's the variable, you have an exponential model. All right, let's flip the lesson over. We're going to compare two exponential models. We're going to look at bacterial colonies. We got colony A and colony B. And the way we're going to compare these is we're going to compare them by looking at the graphing calculator. Now it says that you need to change some window settings and whatnot, but this is for an old graphing calculator. Since we're using Desmos, we'll just get Desmos up and we'll compare them. So give me a second to get Desmos loaded. Okay, we've got Desmos up. We're going to write both equations into Desmos. Instead of using p and t, though, we're going to use just y and x. So we usually have y by itself on the left and x on the right. So our first equation is going to be y equals 100, 2 in brackets. And then to get to the exponent, we have to come down here and hit this AB button. And that's where we can put our x. And now for our second equation, it's pretty much the same as our first one. Y equals 100. The difference here is that the base is 3. And we got our AB button, x. So there we go. If we zoom out here, we can kind of see what happens a little bit better. We have a weird scale. So what we're going to do is I'm going to zoom out a lot more to get more of a vertical scale. But we've got a lot of x going on here. So we really can't see what's happening. So what I'm going to do is I'm going to go to graph settings by clicking the wrench. And if you go to x-axis, you can set the window for the x-axis. And this is kind of what this was saying here to set the window. So we're going to set our x window to go from just -1, and we're going to have it go up to, let's say 10. So we can get a little bit better picture of our curve. And then we'll just click the gear to make it go away. I'm going to play around with the window a little bit now. There we go. That's a little bit better picture. So we can see they both start right here at 100, and y equals 103x, the blue graph, is going up faster than the red graph. So that's what you're supposed to notice there. The growth rates are different. So the base, 2 and 3, those are the only different numbers. So we'll say growth rates different. So what's happening? Well, A is being doubled, and B is being tripled. But the initial value is the same. They're both 100. So what's the doubling graph look like? Well, it's still going up. It's just not going up as fast as tripling. And that makes sense because multiplying by 2, the numbers won't get as big as multiplying by 3. They'll get as big, just not as fast. So this is faster growth. How would the graph change if colony A was changed to 200 bacteria initially? Well, instead of 100, let's make it 200 and let's see what happens. So the red graph now starts higher and goes up, and it's still above the blue graph, but then all of a sudden, right there, the graphs cross, and the blue graph is now above the red graph again. So all it really changes is the y-intercept. Colony A starts at a higher population, 200, but colony B still grows faster. All right, that's comparing models. Let's look at fitting data, so regression, just like in our last two lessons. So we can use exponential regression to produce a curve of best fit. Like a parabola is a curve, so is an exponential curve. They're just slightly different. So sometimes the exponential curve will be better to model data. So we're going to take a look at some data. We've got our years and our population in millions. So we've got years are going to be our x and population is going to be our y. But it says use a graphing calculator to determine the exponential relationship that best fits, where x is number of years since 1921 and y is the population in millions. So these aren't going to be our x's. This is going to be our y. Our x's are going to be how many years since 1921 each year is. So 1921 we're going to call year 0. And then every year, this one's 10 more, that one's 10 more. We're going up by tens. 40, 50, 60, 70, 80. Those are going to be our x's. So let's make our table here. I'm going to get rid of my graphs. One thing you can actually do is you can keep the equation there if you're interested, and you can click the dot and it disappears, and then you can reload it. We'll just get rid of it. Plus, we're going to add our table. So we got our x's and y's. Our first x is 0. Then we get 10. Then we get 20, 30, 40, 50, 60, 70, 80. And our y's, we've got 0.52, 0.69, 0.82, 1.17, 1.63, oops, 1.17, 1.63, 2.18, 2.82, 3.37, and 4.08. Now we got our dots, and let's zoom to see those dots. They're all pretty low there. So what we should do is we should play their scale again. So I'm going to hit my gear. X scale seems fine. The Y scale, let's make it a little bit better. Let's say -1. And the biggest number on the Y's is 4, so let's just say maybe something bigger than 4. Not go 5, we'll give it a little bit more. Let's go 8. And there we go. There's our dots. All right. So now, if we want to run quadratic regression, not quadratic regression, exponential regression, we need an exponential equation. Well, our exponential equation is y equals abx. So instead of an equal sign, we'll use our swivel, a, b, x. But since we're working with y1 and x1, we'll do y1, x1. And there's our model that we'll use in Desmos. All right, and let's make a model. We got y1 squiggle, a, b, and then we want an exponent, and we want x1. And there we go. There's our exponential curve of best fit, and there's our parameters a and b. So I'm going to write this down. A is 0.603816. I'm going to keep all the decimals. And b is 1.02466. So our equation will look like y equals 0.603816 bracket 1.02466 to the exponent x. There's our equation. So what do a and b represent? Well, a, if we remember, is the initial value. So 0.603816. Well, what's that represent? Well, initial value means the initial population. Now, our initial population in our table is 0.52, but that's actual data. Our curve of best fit actually goes above that point. If we look right here, there's our actual curve of best fits above that point. So what's that number represent? Well, this is population in millions, so it's 0.6 million, which is 600,000, or to be more accurate, 603,816, and that's the initial population. And B, 1.02466, B tells you whether it's growth or decay. And since it's above 1, we have a growth model. How much above 1 are we? Well, we're 0.02466, which is 2.466%. So our population is growing by 2.466%. Estimate the population in British Columbia in 1985. Well, that seems silly. Let's change that. Change it to this year, 2020. So 2020 would be, well, how many years since 1921? Well, let's do a little bit of math. 2020 minus 1921 would be 99 years. So we can use Desmos to figure that out. How do we do that? Well, we go type x equals 99, and we go see where we hit the curve. Desmos, click POI, and we get 6.734 million. Or you can use the equation. We have an equation, 0.603816, 1.02466 to the exponent, and we know our exponent's 99. So we can use our calculator. So we got 0.603816 bracket 1.02466 bracket exponent button 99 equals, and we get 6.7345. That's pretty close. Million. So once you make a model, you can use your model to make predictions by typing in any x value, and I'll give you the y value. Also, you can use the equation to do the same. So this is using exponential regression model to make predictions. And that's it for lesson 6.5. One more lesson in this unit, lesson 6.6, where we'll work on selecting the best regression model. Thanks for watching, and I'll see you in 6.6.